let us start this lecture with a thought process from Albert Einstein, who happens to be one of the not only the greatest scientist of 19th century, but also an inspirator for me. So, therefore, I put this thing, his thought process: the concern for man and his destiny must always be the chief interest of all technical effort. I would like to put also say that it is not only the technical effort, any effort as a matter of fact. Never forget that it among your diagrams and equations that we do, and then we forget about the humanity in that. So, we will now be discussing about the some concepts which are very important for the thermodynamic, and in the last lecture we discussed about work, and the way work is defined in thermodynamic is quite different than that of the mechanics, and we demonstrated also that limitation of the definition of work given what you call in mechanics. However, we looked at the thermodynamic definition encompasses all the kinds of work, not only the PDV work, but also the soft work, and then electrical work, surface tension work, and other things. And some of the examples I have not taken also, like for example, magnetization, that you can also, whenever it will magnetize, some work can be done, and one can also define very easily with the definition of thermodynamics. So also the dielectric material, whenever there will be interaction, there will be some work done, and several other things which I have not included because of paucity of time. And today what we will be discussing is basically another form of interaction, what we call it as basically heat interaction. So, if you look at a thermodynamic system can interact with its surrounding in two modes. One is the work, other is the heat. Question arises, what do we mean by the heat? Generally, you can say, look, I mean like I am having a lot of energy to do the work. Some people say, look, I am very tired, I do not have energy, right. And whenever you say that some energy in a little qualitative manner, right, we can say it is hot, or it is the energy content of a body, right, or a material. So, is it really so? Right. We call it as a condition being hot or cold or constitute as the energy content of the body, right, or something like that. But is it really so? Is it the heat is same as that of the energy? Is it so? Or it is similar to the work that we have discussed in the last lecture, that work is basically energy in what? In transient. It does not depend on what you call point, it will be dependent on the path, right. So, therefore, it is a energy transfer, or rather through the form of work. So, however, as I told that energy and heat are altogether different thing in thermodynamic sense. It is not same as that of the what you call energy, because heat is basically not a property of the system, and energy is a property of a system, and it will be possessed by the system, right. Is it heat will be possessed by the system? Generally common sense people say, but in thermodynamic sense we do not say that. So, heat is manifested when a system undergoes a change, right. For example, I will take the example of hot what you call tea, right. If I do that, it is a hot tea, and the ambient temperature, if you look at here somewhere around this point or any other point, it will be what? It will be low. For example, if I say something this temperature is something 90 degrees Celsius, let us say, for example, and here it will be maybe let us say 25 degrees Celsius in this room, because the AC room we might have maintained at 25 degrees Celsius, right. So, there will be what? Heat transfer from the hot T to the its surrounding, right. Yes or no? I can take this as a system, like simply a system, I can say this is my system kind of thing, and there will be heat transfer, right. So, therefore, heat transfer takes place due to what? Due to temperature gradient, right. So, and then one can say basically heat transfer, right, that in thermodynamic sense we call it basically the heat. In this case, energy transfer takes place till it attains the thermal equilibrium, and like if the heat will go, if heat will will be transferred this, and then what will happen? The temperature here it will be dropping down, and here there are nearby this place it will be going up like 25 degree, maybe 30 degree nearby, not very far away from the cup of the hot tea. And then whenever it will remain, both the temperature will be same, both the system. So, if it is this is my system, right, and this is your surrounding, then what will happen? There will not be any change of heat transfer, no energy will be transferred due to temperature gradient. So, therefore, we can define the heat as an interaction, energy interaction between system and surrounding due to temperature gradient, right. So, in the work whatever the things we are doing, there are several gradients we talk about, like there will be what you call surface tension, there will be pressure gradient, there will be magnetization or dipole effect or electromotive forces, these are all gradient, right. So, but here the heat is due to the temperature gradient, there will be energy interaction, that we call it as a heat. So, if you look at basically heat in thermodynamic sense, right, can be defined as a energy in transit, it is similar to that of the work. So, what are the differences between work and heat? In case of heat, it is due to temperature gradient, right, and whereas others will be due to other various gradient like pressure gradient, concentration gradient, pressure gradient, and then maybe what you call electromotive forces and other forces like surface tension, other thing. So, heat is also a path function like work, it will be dependent on the path it takes, and in the differential form we call it as delta Q or Q12, any symbol we can use, 1 2 will be more specific, that means it is between the state 1 to the state 2 or. So, therefore, the heat per unit time we call it as a kilowatt, that is kilojoule per second in SI unit, and specific heat transfer we will be using like which is heat per unit mass, and we will be also using heat per unit mole, right, depending on the problems, depending on situation. So, as it is what you call heat is basically a is it a extensive property or intensive property? Is it is it a property of the system? No, right. So, but whereas energy is a property of the system. So, here we will be using the symbol like like a direction wise, and that if the heat is coming from the surrounding, right, to the system we call it positive, and when the heat is going from the system to its surrounding or heat is transferred by the system to its surrounding, right, we call it negative. Keep in mind that in some book people use different sign conventions, just opposite of that. So, that really does not matter if we use a consistent what you call sign, That means, if you look at the work done by the system, what it would be? Work done by the system, whether it will be positive or negative. According to our sign, it will be positive, and work done on the system will be negative. But in case of heat, it is just opposite. Heat is transferred to the system is positive, and heat is transferred from the system to its surrounding is negative, just opposite. In some book you may find just opposite of that, like heat transferred to the system is negative and heat transfer from the system is positive, and then work also done will be just opposite of that. Okay? Are you people getting confused? What I am trying to say that if you do this sign convention properly, then it is it will be same. So, we will be using the sign convention, and let us look at the heat in thermodynamic sense. Whatever we have discussed till now, it is equal to the heat transfer, kind of things, and heat transfer can occur by the three modes. All of you will be knowing heat conduction, heat convection, and radiation. I will just give some example, like, and then tell that what is that. Like, if you look at, if you touch a pan which is on a stove or a hot plate, in this case it is a hot plate, right, and then what will happen? You will feel hot, right, it will get burned if it is very high temperature, right, and that is due to what? Due to contact. By contacting a metal, right, we get the heat, and that is what we call the heat conduction. In case of heat conduction, energy is transferred by direct contact, right, and of course, it will be some laws will be used, and that laws of what you call Fourier's law, and then we will be also, let us look at the what you call convective heat transfer, where if you take a pan and there is a hot water here, right, and when this is come in contact, the lower bottom portion of this pan with the hot plate, and it will be heated, and then water will be going up, and then of course, it may be cooled by transferring, and it sometimes it will vaporize also, and as a result the energy is transferred by the motion of molecules, because we know that when the molecule will be receiving the heat, it will be moving at a higher velocity. So, it will be moving up, and that we call it as a heat convection. And heat radiation, we know that we use in the winter, particularly we will be using heating or getting heat from the fire or some other heaters, resistance heater kind of things, and then we can, even though we are sitting out away from the heating source, we can get heat, and we get radiation in all the times. So, that is basically the heat in energy transfer due to by the radiation, and this contains some electromagnetic waves, and then like that we call radiations. So, it will be all combination of the heat conduction, convection, and radiation which will be taking place, and that makes the heat to transfer kind of thing. So, if you look at the two modes of energy transfer, work and heat, depend on the choice of the system what you consider, right. Let us take an example, like, because like whether the work transfer or heat transfer, how you will define in a system, will be dependent on the how you have chosen your system, otherwise it will be different. For example, I will take this system, right. If you look at, this is a heater, right, resistance heater you can say, and it is connected to a battery, and then you are heating the water, right, and this is our system, right. Now, system which one I will take? So, whether I will take the water, I can take water as a system, exclude the heater, exclude the heater, then what will happen? I can choose just the water which include I can take the water along with the heater. There is a system I can think of, am I right or not? For example, if I take this as my system, that is the water, only water in this case I have taken, I have excluded this as my heater from this. What it will be? Will it be work or will it be heat interaction with what it would be? I told you I can take two systems in this case. One is water, only water. In this case, only water I have taken. I have excluded the heater from the system, right? And I can take another system which include not only the water, but also the heater. So, which case it will be work, which case it will be heat? That is the question. Are you getting? So, in this case, as I told, the system is basically water and the surrounding will be heater and battery, right. The interaction will be energy transfer and due to temperature gradient. If there is a temperature gradient, because the surface temperature here, if you look at it, will be very high and then there will be heat transfer to the water and then you call it as a heat interaction, right. But if I take the other kind of things where only the water as my system, not only the only water, but also the heater as a part of the system, then what it will be? That will be work, because you can think of that heater and being replaced by a motor and then it is with a pulley, it is raising a mass and then going through the gravitational force field moving, and then you can call it as a work done, am I right, according to the thermodynamic definition. So, therefore, that will be the what you call work interaction. In this case, heater and water is your system and surrounding is your battery, because that is the giving the what you call electricity, right, and that will be converted into mechanical kind of thing. One can conceive that and then one can say it is a work done, right. So, what I am trying to emphasize here in this case by taking this example, that it is important to choose proper system boundary and also do the proper analysis, identify whether it is heat or work. Otherwise, suppose you have chosen the heater what you call water as your boundary, system boundary, like water only you have considered as a system, and then you are saying it is work done. So, naturally you will be wrong. So, therefore, one has to be careful about that. Let us look at another example, like what you call there is a paddle wheel which is rotating, right, and then it is connected to a what you call pulleys and to a mass which is moving against the gravitational. Therefore, what will happen? It will be rotated and some work is being done, right. And when this work is being done, what happened to its temperature? Will it be remaining same or it will be different? Will it be lowered down or it will be decreasing, or sorry, where it will be decreasing or whether it will be increasing? It will be definitely increasing, right. So, let us say instead of that I will take a system where you are putting some kind of a heat, and then whatever temperature, let us say it will be started with 25 degrees Celsius here, in it has gone to 30 degrees Celsius, and here it has gone also 25 degrees Celsius to 30 degrees Celsius. And then I will what you call I need to identify whether it is a work done or whether it is a heat being transferred. Is it possible? Actually, it is impossible to know the mode of energy transfer once it is completed, right. Once it is completed, you do not know really whether it is a work done or a heat transfer, or whether the energy transfer has taken place through the mode of heat or the work. So, that thing you should keep in mind. So, what are the similarities between the work and heat? Let us summarize it. What are the similarities? What are those? Both are energy transfer in transit, right? Yes or no? Both are path function, right, or inexact differential, and both heat and work are boundary phenomena. It means it is takes place, all this transfer takes place through the boundary of the system, right. And system never possesses either the heat or the work. Then what does it possess? It possesses the energy, and which is the property of the system. So, these are the similarities between the work and heat. Okay. So, just to summarize the sign convention, I am just again repeating, the work done by the system is positive and work done on the system is negative, and heat transferred to the system from its surrounding is positive, and heat given by the system to its surrounding, right, is known is negative, right. So, these are the convention we will be using, but however, you can make it just opposite, just opposite, then that does not matter. Whenever you are applying this thing to the thermodynamic relations, it will not be really having any consequence. So, now we will come to a point to discuss about how to specify a thermodynamic system, because it is important for us to specify a thermodynamic system, as there will be interaction between the system and its surrounding. As a result, there will be certain amount of matter which will be affected by this energy transfer, right, and this we need to look at the properties, and hence a system can be specified by the composition of matter, right. For example, if I consider the air, right, how many moles of oxygen and how many moles of nitrogen will be there, we need to look at it. Similarly, we need to look at what is the energy content of that matter at a particular pressure and temperature. If I take an example, of an ideal gas which is at a particular volume, certain amount of gas is there and at a particular temperature. So, therefore, I should also know the measurable properties like pressure, temperature kind of things, and I should know the volume, I should know what is the energy content, and I should know the composition of the matters, right. These are the things are required to specify a system. So, by specifying these quantities, the state of the system can be defined, and for example, like for an ideal gas, we know that P v is equal to N RU T, RU is basically gas constant. That means, it is basically function of pressure, volume, temperature and number of moles, right. Okay. So, therefore, we need to look at like properties of this, and but question arises, how many variables can be varied independently. For example, if I take an ideal gas, if I increase the pressure, what will happen to volume, right. If I increase the pressure, what happens to temperature? Can I vary it independently, So, that we need to look at, and thermodynamic properties basically are related to energy and its transformation, that is the crux of the thing. So, we need to look at that number of independently variable properties will be basically equal to number of ways by which energy of the system can be varied, right. We can make a guess out of that. That means, that how many ways we can vary the energy of a system, right. So, let us consider the gas in a piston cylinder arrangement, and this we call it as a system, the dashed line, and we are put to identify the system boundary, and it is having certain weight kind of things. So, what will happen in this case, the work energy transfer can be take place by what? By PDV work, right, is not it? So, if the piston can move up or the down, some work will be done either by the system or by its surrounding. Okay. And there might be also some heat interactions. So, therefore, in these situations what we will do? We can say that by the two mode the energy of the system can be varied. Similarly, if I take an elastic bar, then there will be applied a force and then there will be a stress here, right, and if you look at, if I apply a force, it may be elongated. If it is elastic resin, it will be elongated, and if you remove this force, then it will be come back to its original position, right. Similarly, if I will heat a metal rod, what will happen? It can also be expanded, and again it will contract, provided it is a very small change in temperature or the heat you have given. The heat interaction is not too strong, right. You might be knowing that when you are using very high temperature or the gradient kind of things, it may not, it may bend, right, or it may not come back to its original position. So, therefore, in this case it is basically by the stress or by the heat interaction. So, if you look at, I mean we need to look at basically how many thermodynamic property has to be varied independently. Let us take an ideal gas, again same example. What we will do? We will keep this thing in a hot bath. Let us say there is a something hot bath here, right. This is the hot bath. Hot bath means it will, the temperature can be maintained at a constant, the temperature can remain constant, is a big, like you can think of what will be a hot bath. Let us say it should be having a very large amount of mass at a particular temperature, so that if any heat interaction will be taking place between the system here and its surrounding. So, this is my system and this is my surrounding, then that temperature will not change, right. Are you getting? For example, if I put take some kind of a, let us say hot rod which is at 70 degrees Celsius and put into a pool. Pool means very big what you call water pool, and then what will happen? The temperature will not change at all as such, okay, of the total water. So, if you look at the this temperature at the constant bath, the gas can be compressed by changing the volume, right. I can put a weight and then it can come over here, right, the piston can move and then the change in the volume. So, that means there is a interaction between the system and surrounding, and in this case temperature remaining constant. That means energy is constant while the volume is changing, right, is not it? The energy is of the system will be remaining constant because the what you call the temperature is remaining constant, right. Energy basically I mean internal energy. So, let us take another situation where we are giving the heat and latching it such that the piston will not move and the volume is remaining constant. So, therefore, energy is changed now. See, in that case energy not changing in the earlier example. Now, it is changed due to the heat transfer. However, the volume is remaining constant. So, hence one can say that energy and volume can be varied independently for a compressible system, because this is what we are discussing now, a compressible system where you can compress it, right, or you can expand it. So, when energy and volume can remain constant for a system, which is the thermodynamic property that can vary independently, right. So, then question arises like which is the thermodynamic property that can vary independently. We will have to look at it. So, let us other variables like pressure can be changed independently, like when this is changing, like one can think of changing the pressure. We know that the pressure of the gas can be varied by 3 more ways. I mean, like one is by compressing, that we know, right. If I compress a gas, the pressure will increase, or I can fix the volume, then I will heat it. In the last example where the piston is being latched, that means volume not, and when I am heating it, what will happen to pressure? Pressure will go up. Am I right or wrong? So, similarly, if I will keep the volume constant and vigorously stir and give some work, what will happen? That again pressure will go up. So, if gas is compressed, then volume is decreasing and energy remaining constant, right. And by heating, what is happening? Energy can be increasing while volume is remaining constant, right. And in stirring, what is happening? Energy is increasing while volume remain constant. This similar heating, one is the work, you can think of stirring is nothing but a what you call shaft work kind of things, and in the other example it is the heating. And if you look at the change in pressure alters what it does, either energy or the volume. One cannot really keep both as a constant. I cannot really make the volume and energy constant, right. You cannot do that. So, therefore, we can say that every mode, work mode, one thermodynamic properties can be varied, either heating is one of the mode and other is your work. In this example, stirring is the work and heating is the heat transfer whatever taking place, and that is basically 2 mode. So, for every work mode, one thermodynamic property can be varied independently, that is only valid for the compressible substance. Okay. What we were using simple compressible substance. So, the work mode is basically the generalized displacement which we have discussed can only be varied independently, right. For the work mode, the you can vary the displacement, generalized displacement. It need not to be PDV work, it can be shaft work, it can be stretch or the surface tension, stretch due surface tension work, it can be magnetization, that can be varied independently. So, therefore, we can say that if the system has several reversible work mode, then number of independent thermodynamic variables is basically number of the reversible work mode plus 1, right. 1 will be basically the heat, one can think of. So, and that is nothing but the state postulate, which will help us to say that how many variables can be changed independently. That is, for a given thermodynamic system, the number of independent variables that can be changed, variable I mean the thermodynamic properties, is equal to number of reversible work mode plus 1. So, let us consider that if nth reversible work mode is there, then number of independent thermodynamic properties are basically equal to n plus 1 for complete description of the system. If we consider a simple compressible system with a single gas, one can think of is basically number of thermodynamic properties that can be varied independently is equal to 2, because one is the reversible work and other is one reversible work plus 1. But if system contains n moles of gas and system can be described by completely internal energy, volume, number of moles, but if system contains mixture of gases, the variable will be more depending upon the number of kind of gases will be there and which will be required for specifying a system completely. So, what we will do, we have talked about basically how many variables and other things. We will just quickly look at what do we mean by temperature, because whatever the heat transfer or the heat interaction is taking place between the system and surrounding, it is due to the temperature gradient. Therefore, we need to understand what do you mean by temperature, right. So, generally we use temperature very often in our vocabulary. Whenever we talk, we say that temperature is increasing, decreasing, but what do you mean? Like we can say it is a basically hotness or a coldness kind of thing. It is a measure of hotness or coldness. Some people can say look warm or hot or the red hot, right, and that is with our senses, right, and our senses may be misleading. For example, if now let us say it is hot quite and summer, hot summer. Now, you are sitting now on a wooden chair. Let us say there is a wooden chair in the hot summer outside, not in the AC room, right, and you will sit down there. What do you feel? It will be hot or there is an or not. There is another chair in the same place it is being placed. One is made of metal, one is made of wood, right. So, if you sit down there, the same person, and what do you feel? Which will be hotter, at least according to your sense. Which one? Metal will be hotter. Why? Because both are at same temperature, right. So, therefore, it is misleading, because your sense, the same sensor you are using, and then it will be misleading kind of things. So, but however, we need to talk about the temperature, like what we will be doing, we will be looking at this example with the copper block at 150 degree Celsius, and there is another copper block at 50 degree Celsius, and it is having a partition, right, which is separating, and that partition is being removed, and this both the block will be coming in contact with each other. So, what will happen if this block is removed, right, and then the heat the heat from the higher temperature will be passing through the copper block, which is at the lower temperature, right. And if you allow a large amount of time or the sufficient amount of time, what will happen? It will reach a steady state temperature, and of course, it will be changing with respect to time, but if you give enough time, then it will reach a temperature and is already insulated. So, we can call it basically it has reached a thermal equilibrium, right. So, and that is we can state in a very different way. We do use this thermal equilibrium in our day to day life also, right. Let us say that this block A is in thermal equilibrium with block B, right, and we can also conduct experiment and also do that, like in the block C is in thermal equilibrium with block B. Then we can say that the block A is in thermal equilibrium with the block C, and that is nothing but your zeroth law of thermodynamics, which was given by R. H. Fowler in 1931 and much later than the first and second law of thermodynamics. That means, before this law being put forwarded by the Fowler, the first law and second law were being put forwarded by the Joules and other people, right. So, if you look at what is that 0th law of thermodynamic, if two bodies are in thermal equilibrium with the third body, then they are also in thermal equilibrium with each other, and this law is basis for the temperature measurement. We know that you must be having experience in your day, in your life, that is if you place the thermometer, right, on your armpit whenever you are having a fever to measure the temperature, right. So, you will take a more time, am I right, is not it? Instead of if you put in that thing in your mouth where the liquid will be there, right, and it will take less time to reach the equilibrium temperature, is not it? Suppose before time if you remove, then you will so it will not show you the your body temperature, it will be showing the lower than that, right. So, that we use for the temperature measurements, and if you look at the various ways of measuring temperature, and right, there are three ways I am just trying to discuss over here, and in each three cases, right, that we will have to satisfy the thermal equilibrium governed by the 0th law of thermodynamics. If you look at, if this thermometer which what you use is a mercury in a glass tube, and you can use also some other kind of things, like if you look at this temperature here which will be shown, let us say the mercury will go up, and then that label because of expansion of mercury whenever it will be come in contact with the body, right. Body means in the matter anything, you can also use this thermometer, but this is having limitation of this thermometer, this is a glass tube thermometers, and you can also go for a what you call a thermocouple, where two dissimilar metal when it joined together, and there are two junction, one is we can call it as a hot junction, right, because you can put into a flame or some other higher temperature, and then you can make it as a cold junctions, and then maybe ambient temperature, then there will be what you call Seebeck effect, and that gives you EMF, and that if you measure that EMF, then you can relate that thing to the temperature, provided this cold temperature, and generally people use ambient or the 0 degree Celsius or the ice point being used. And there is a change in the resistance if due to the temperature, you can use a what you call Weston breeze, and then change these variables, and then you can measure the temperature and that. So, if you look at basically one can measure, and there are several various other ways of measuring the temperatures, but all the time it has to be satisfy the thermal equilibrium condition, then only one can. But if you look at we may measure, because these are all variables, like if you look at temperature is an intensive property or an extensive property, intensive property. So, in intensive property we need to assign a numerical value to the thermal state of the system to define the temperature scale, right. Otherwise, we cannot, like for example, like if you take a mass, right, or a volume. So, which are extensive property, you can this thing. So, therefore, we need to look at temperature scale, and temperature scale is established by assigning numerical value to reproducible states. This has been done, like and two reproducible state which are being used very much. One is the ice point, other is the steam point. And ice point, if you look at the temperature of ice with air saturated water at 0 degree Celsius being considered, and the steam point is the temperature of pure water with its vapor at 1 atmosphere pressure corresponding to 100 degree Celsius kind of things. And Celsius have used these two points, ice point and the steam point, and then found out a Celsius scale, what we call degree Celsius, and nowadays also we do use. And similarly, the Fahrenheit, he assigned some value to the ice point to 30 degree Fahrenheit and the steam point to 212 degree Fahrenheit and made a scale. So, that is known as Fahrenheit scale. However, these scales will be having the problems because the different materials have different temperature volume relations, right, and temperature scale based on the change in volume of material of mercury what we use in our day to day thermometers will be different than when we are using water or some other things, right. So, therefore, if we use the mercury in glass thermometer and alcohol in glass thermometer or copper constantum thermocouple or a platinum resistant thermometers, then you will find the temperatures will be different. So, if you look at these temperatures are different, of course, you may say look it is not really much, but however, preciseness is very important when you do conduct measurements. So, therefore, it is important to devise a thermometer scale which is independent of the material, that is very important, right. So, whether it is possible or not, we will see that we can think of a constant volume gas thermometers which will be this is your containing gas which will be in a system, I mean like you can say this is your temperature bath which will be, and whenever the temperature will go up this portion what will happen, this is having a flexible mercury which will go up and it will go up that distance I can connect it with the temperature over here whatever it is having, provided this system will be in thermal equilibrium with the water bath or the temperature bath, right. And so, if it is so, then what we will call if I say this volume is constant, because if I will keep in such a way that the volume of this gas of this system what I was saying, the bulb of the thermometer is constant, that means this pressure is proportional is the temperature is proportional to the pressure, isn't it, and that head which can give me the temperature whatever changes will be occurring with this thermometer. So, triple point of the water has been accepted as a reference point internationally because of fact that all three phases solid, liquid and gas coexist simultaneously. If there is a small change in any of either pressure or temperature, then there will be change, the three phases will not be there, that may be two phase or maybe single phase depending on situation. So, therefore, that is very precise definition and triple point of water is considered as a 273.16 Kelvin at 1 atmosphere pressure, and it is considered to be the superior as compared to the what you call ice point or the boiling point. And if I will use the ideal gas law and T is proportional to P at a constant volume, then T by T T P, that is corresponding to the triple point, is equal to P by the P T P, and I know this temperature T T P is known, that is 270.16 Kelvin. So, therefore, the temperature I can really relate to the pressure provided I know the P T P, which is also very precise. So, you can think of by conducting experiment and plot this calculated temperature for P by P T P, and whether it is the helium gas or the nitrogen gas, if you look at a lower pressure, it will be coming to the same temperature kind of things. All gases, I have taken nitrogen or helium at a low pressure, it will act like a, and though what I say you can extrapolate and put that temperature, and that is being considered as a what you call ideal gas thermometer. And of course, it is having limitation that you cannot go beyond the temperature or the below that temperature where the gases can liquefy. If it liquefy, you cannot use that, that is the limitation of ideal gas thermometer. So, above that one can use. So, among all these gases, helium has the lowest boiling point, that is 4.21 5 Kelvin at 1 atom space, we set the limit on the range of thermometer. Of course, at the high temperature gases can dissociate, and if you look at international practical temperature scale was introduced in 1968, and they use a Kelvin thermodynamics temperature scale, which will be valid over all temperature ranges, which is independent of property of the thermometric fluids. That means, whether you are using mercury or water or any other things. So, it will be not, and that is basically temperature, Kelvin can be related to the degree Celsius, we just add to 70 degree 0.15 Kelvin. So, if you look at, we will be discussing about this ideal gas temperature scale little bit whenever we are talking about second law of thermodynamics, which we will be discussing later on, and we will basically looked at the how heat is is a one form of energy interaction, it is a basically path function, and then we look at various way of temperature measurements, and then we looked at how we need to have a practical temperature scales that we need to use it, and that we will be using basically the Kelvin in our case. So, with this I will stop over. Thank you very much.